Assalamualaikum and greetings to everyone. So we will presenting about application of differentiation related rates. For the program code, it is MAT183, which is calculus 1, and we are from group AS124. We can see the presentation is divided into section, and this is the first page. It seems the presentation is being created by a team, as there is our team member section. First, we have Akifuddin, then Haikal, then myself, Darwish, and then another one person is Islam, and then we are from group 5. Let's take a closer look at this presentation slide on related rates. The slide is titled Introduction, and it's part of a larger presentation on calculus. The text on the slide explains that related rates problems involve quantities that are connected to each other. The key idea is that related rates help us determine how fast or slow a certain quantity is changing by using the rate of change of another related quantity. Let's explore this slide titled Why We Use Related Rates. This slide highlights the significance of related rates in understanding and analyzing real-world systems. It states that many systems in the real world involve quantities that are constantly changing over time. This could be things like the position of a moving object, the volume of growing organism, or the current in an electrical circuit. Related rates provide a powerful tool to analyze how change in one quantity within a system affect other related quantities. This understanding is particularly valuable in fields such as physics, engineering, and biology. Then I will pass the next part to our brother Akif.
Let's explore this presentation slide on the step to solve related rate problem. This slide breaks down the process of solving related rate problem into 5 key steps. Step 1. Decide what the two variables are. The first step is to identify the two quantities that are changing and are related to each other. This could be things like the radius and volume of a sphere, the height and base of a triangle, or the distance between two moving objects. Step 2. Find an equation relating them. Next, we need to find an equation that connects these two variables. This might be a geometric formula, a physics law, or some other mathematical relationship. Step 3. Take d over dt of both sides. This step involves differentiating both sides of the equation with respect to time. This is where the chain rule is often used. Step 4. Plug in all known values at the instant in question. Once we have the differentiated equation, we plug in the value of the variable and their rate of change that are known at the specific moment in time being considered. Step 5. Solve for the unknown rate. Finally, we solve the resulting equation for the rate of change that we are trying to find. Let's analyze this problem statement related to related rate. The problem scenario involves sand pouring from a cube and forming a conical pipe. We are given information about the relationship between the height and radius of this cone. We know that the height of the cone is 3/4 the radius. We are also told that the volume of the sand pile is increasing at a constant rate of 4 cubic meter per second. The question we ask to answer is how fast is the radius of the pie changing when the radius is 4 meter? The solution I will pass to my friend Haikal.
Now, to solve this problem statement, first step is we need to gather in the given information. First, we are told that the height of the cone is 3/4 the radius. We also given that the volume of the cone is increasing at a rate of 4 cubic meter per second. And we are asked to find the rate at which the radius is changing, or dr over dt. And let's jump to the next step. In step 2, we start by expressing the volume of the cone, V, as a function of its radius and height. Since the height is given as proportional to the radius, with h equal to 3/4r, we substitute h into the volume equation, that is V equal to 1/3 pi r square multiplied by 3/4r. After that, we need to simplify this equation to get to pi r cubed over 4. After that, we have to find the derivative of V with respect to r, or I can say is dV over dr equal to 3 pi r square over 4. In step 3, we need to determine the rate of change of the radius dr over dt using the chain rule, as you can see in the slide. After that, we need to substitute the given values so that we can have the equation like 4 multiplied by 4/3 pi r square, and simplify the equation for radius equal to 4 and evaluate the terms, and thus the rate of change of the radius is 1/3 pi meter per second. And that's how we derive the rate of change of the radius. Now I will pass the next slide to my friend Islam.
Let's wrap up with the conclusion of this lesson on related rates. As we have seen, the heart of a related rates problem lies in understanding how the rates of change of different quantities are interconnected. The solution to a related rates problem describes how a particular rate of change depends on others. For example, in problems involving geometry, like the radius of a circle or the height of water in a tank, the conclusion often explains how one dimension's rate of change impacts another based on their mathematical relationship. So, remember, when tackling a related rates problem, focus on identifying these relationships and using the chain rule to connect the rates of change.
That's all for our presentation. To summarize, we explore how to calculate the rate of change of the radius of a cone when its volume is changing at a constant rate. We walk through the derivation step by step, starting from the formula for the volume of a cone using the chain rule and substituting the given values to find the solution. I hope this presentation clarified the process for you, and thank you for your attention. This is our reference for this slide.